Okay, guys, welcome back to the That City Academy's calculus series. I think we didn't get a chance to meet you guys for a long period of time. We're going to come back to Calc 2, Calculus with Analytic Geometry, Part 2. And we have sometimes you're going to encounter with the heavy questions. Sometimes you're going to struggle with it. With the aid of that coming from my side, that you don't have to struggle anymore, that you could go through all the steps very clearly and then write down everything very clearly and then use all the algebraic notation very clearly and use the calculations, computations very clearly and stick to all the rules, theorems and theory and everything very clearly. That way that you're going to come up with like a very nice answer at the end of the day, the perfect answer. That's what we are looking forward to seeing at the end of the day. That's what we really need at the end of the day. So you're gonna to get such an answer at the end of the day, an exact answer, perfect answer, without any flaws or any kind of mistake. We have to look into some kind of example and see that how I am been doing over here, and that way that you can easily follow the same way and then just get heavy calculus questions even easily done. And let's look at this example, okay? I'm gonna write this one very clearly over here. You just look at it's the question. Q stands for question. A bead is formed by removing. I'm going to write that uppercase R to distinguish my simple R. But if I'm going to write the simple R, it looks like a V sometimes. So because of that, I'm going to write uppercase R all the time. Okay? So formed by removing a cylinder being characterized, being given with the aid of its radius of, okay, 3r, be careful, 3r, that's the radius of the cylinder. This is the radius of the cylinder. We're going to come back and then elaborately discuss everything later on. For the time being, just have a look at it. See, 3r from the center of a sphere. Even for a sphere, it will be completely characterized by its radius of 4 uppercase. Careful. This is kind of a little bit tricky question. Okay. Here we have 3r. This whole thing is the radius of the cylinder. This whole thing is the radius of the sphere. Okay. Find the volume. Find the volume of the bead. Because they are forming a bead from a sphere by removing a cylinder from the center. Then the leftover has some kind of a volume. That's the volume they are eyeing for. Bead with capital R equals 2 and simple R equals 1. See, this is how the question reads. It reads like this. It's kind of like a little bit trickier than from the standard questions. So, but you don't have to worry about anything. That's why we are here. That's why we are here to help you out, to get the answer, but going through all the steps one by one. Okay. With the aid of this, all the steps, eventually you're going to get a nice answer. let's see, it's a bead. It's then I had to tell two things. Okay, are using, I'm going to say, okay, find the volume of the bead are by using, I'm going to add one more thing. By using first one, shell method. The second one, you have to get this done using two methods and the washer method. Shell method and washer method. So you have to get the answer by utilizing this technique as well as the other technique. Okay. So shell method, you are very familiar with the shell method. In addition to these two methods, there's another method called very often been found in Calc 2, the disk method. This is actually, it's some kind of extension of the disk method, which is a washer method. It's a shell method. So there are three methods being heavily discussed in Calc 2. Here we are utilizing shell and washer method because the middle part is gone. It's a cylinder. Cylinder has been removed in order to create a bead from a sphere. Okay. Okay. Before we're gonna get into this one, let's draw like kind of like a picture and get a clear idea. Okay. Don't worry about this one. 3R, see, and 4R. This is the from here to here. That's the radius of the sphere. This is the radius of the cylinder. This is the radius of the sphere. Make sure. Okay. Okay, let's go ahead and draw this one very clearly. Then we can then answer systematically one by one. Okay. Okay, let's say we are using the shell method. First one, we're trying to find the volume of the bead, which is formed by removing a cylinder from the center of a sphere. See? That's the sphere. Okay. Three-dimensional sphere being drawn on a two-dimensional plane by a circle. See, that's a sphere. Okay. What they did was, it's a center. Okay. They took out, okay, they removed cylinder. See, cylinder from here. Kind of like that. See, this cylinder has been taken out. Excuse me. That cylinder has been taken out from this bead. This is the bead. This is the sphere. Now you're gonna get the bead here. See, this part, and even on this side, it has that the cylinder is like, see, something go like this into that whole sphere. See, this is a sphere. See, I'm gonna like not with the same radius, with like a different radius lesser than the radius of the sphere. I'm gonna take out like a middle portion, which would be a cylindrical shape with the radius that is completely less than the radius of the sphere. Okay. So I'm going to take that part out. This is the cylindrical part. This is the sphere. So then we know from here to here, look at, that's the radius of the sphere, or the same. Okay, draw this to a scale. The same way over here too. You don't have to draw every direction and then show that it might then have the radius on every direction from here to here to here to here, here to here. Anyway, same radius. That's the radius. Okay. In addition to, you have a radius for cylinder as well. See. Okay. Therefore, I'm going to take this one as like my axis of symmetry. See. That's like my axis of symmetry. I will call this one axis of symmetry, or axis of rotation. I'm going to use the abbreviation AOR. Axis of infinity, I'm going to use the AOR. So this one, you know, radius, I hope you can see. Can you see? Yeah. Radius of sphere is capital 4R. I'm going to denote that by R prime for my convenience. Later on, I can plug in something. So this is my R prime. The radius of cylinder. Simple 3R, no, simple 3R. That one I'm going to denote by R, simple R prime. R prime. That's R prime. Simple R prime. Okay, that's the same thing. R prime. See. Pretty much that's all. See, make sure. Normally we're going to denote the radius by R. That's not the way how I'm doing, because they have given the radius of the sphere as 4R. R is like the algebraic notation, algebraic value. It can be replaced by the values being given at the end of the day. Here in this case, the R has been given for capital R. It's been given 2, simple R has been given 1. But anyhow, rather than working with 4R, it's easy for you to work with R. Don't use R prime, because R already been utilized over here. That's the tricky part. Here too, don't use capital simple R again here to talk about the radius of the cylinder. Just say R prime. See, with the aid of these two, you can play around and then get all the calculations and computations. And at the end of the day, you can easily replace R prime and R, capital R prime and simple R prime. Okay. So what are you going to do? According to the shell method, if the way that we are doing, if there's some kind of area you're going to rotate around a certain axis of rotation. Axis of rotation may be either x-axis, y-axis, or any axis parallel to either y or x. Doesn't matter where they are. Axis of rotation may be anything. We're never going to talk about the slant axis because at this stage. But even on the slant axis, we can get this done, but we don't go that far. We don't have to worry about that. For time being, we know that's the way we did. We got some kind of area under the curve. We drew a curve. Can you remember? Function being given. See? We're going to draw some kind of a curve like this. See? The function has been given y equals f of x. You can remember. See, this is y. This is x. This function has been given, let's say for instance, it's x squared or something. Later on, what they did was they asked you to find the area under the curve from a certain place to another place. Let's say from x equals 1 to x equals 2. You are looking for this area under the curve. Area under the curve. You know how to get this done. In order to get this done, you simply did was that you took a small strip, okay, either this way, horizontally, or vertically. It depends on the which way that you're going to take it. I'm talking about when it's come to the area. Okay, I'm not going to detail that one. But right after that, you are done with that, finding the area of that one. They're going to ask you to rotate this one either around this axis or y-axis. That would generate some kind of a three-dimensional figure for which that we have to find the volume. That is how we're going to do in the previous example. Normally the curve has been given. What you're going to do, you're going to rotate it, and with the aid of either shell method, washer method, or this method, you're going to find the volume. But you think about that this much. If you rotate this one around y-axis, see, to get the volume, see, you're going to have something like this on this side too. This side too. If you rotate, you're pretty much going to have, and this is the axis of rotation, axis of symmetry. See? You're going to have something like this. See? That kind of a three-dimensional figure you're going to have. See? In the middle will be something like this. Here, something like that. See? Like that. So to get that done, what you did was you pick if you are planning to use the shell method, you're gonna take something, some kind of a small strip parallel to the axis of rotation. Parallel to the axis of rotation. This is the axis of rotation. Here you are. I'm talking about if this area has been given, we're going to ask what would be the volume of the three-dimensional figure when this area being rotated about the y-axis. Okay, for such a scenario should be remedied or answered or should be tackled by taking, if you are planning to use the washer method, some kind of a small strip parallel to the axis of rotation with the width of Ex and height Y. See? At the distance of X at a general point. As a general point, see, the general location, see, you pick the point from here. So you're going to travel X distance, Y distance, pick over here, and little bit infinitesimally small strip you're going to pick from that point parallel to the y-axis. Okay, parallel to y-axis. That's the way that how we're going to do that. Then later on, y can be easily replaced with f of x. In this scenario, f of x would be x squared. But when you apply the same technique over here, that's called the shell method. See, then what you're going to do, you're going to take this out, take this only the strip out, and rotate about axis of rotation, which is y. Then that would generate a small cylinder or shell. See, shell, actually shell. See, like that. If you rotate that one, this part, rather than rotating the whole thing, whole area under this curve from x1 to x2, I'm gonna pick a small piece and rotate about this one. See? So this one would be y, this one will be dx, this length would be x. See? You can see. This is y. See? This is y. This is x. This is dx. It's the same thing. I took this out strip, rotate about the xy axis to create, by rotating that one, you eventually got a shell, cylindrical shell. Cylindrical shell like that. With the thickness of dx and the height of y and radius of x. That same thing I'm trying to apply over here, the same technique. Look at what I'm going to do. I'm going to pick a, see, you don't have to rotate. It's the rotation has already been done in this case. Because it's already formed a three-dimensional figure. What we have to do is just simply pick a what? Small strip like this all the way down to here. Very similar to that one. And rotate that one. That would give you kind of like a what? Shell. If you stack shell from this place to all the way to that one, that would cover the whole volume of the bead. Bead is this area, okay? On this area, this is hollow. The center is hollow, it has been taken out. You see? It's the bead. This area is the bead. Here, this area is the bead. See? That's the bead area. That's the volume they're looking for. So to get this done, what I'm gonna do, I'm planning to use shell method, thinking that I'm using shell method. I'm gonna pick a small strip from here and rotate it O. I'm gonna pick a shell with the thickness of dx at a distance x from here. See, let's call this one 0 for your convenience. X from here with the thickness of dx. See, thinking that this would be your x-axis. So x-axis. Thinking that this would be your y-axis. That's the axis of rotation. So this, the only thing you have to do, find the volume of that shell only. See, it's like this. Okay. That shell. Let me erase this one. Consider, I think we can say, consider. Oops. Cannot see. We have to wait. And consider shell of width dx dx and height. Let's see what would be the height. Height of, see, we're talking about this from here to here. So my convenience, I'm going to say this one h. So it should be 2h, no? Should be 2h. Height h. Okay, height, so 2h. 2h, okay, height 2h. At a distance, dx, height 2h, and radius. Radius. And radius. Radius of, what's the radius? That's x. Radius x. See, that's the radius x. Okay. See. That means we have taken this out, taken out. It looks like this. This is the axis of symmetry. That's the y-axis. Okay, this is y-axis. So this is 2h. From here to here, anywhere from here to here, x. And thickness dx. Small thickness dx. X. At a distance, x from the y-axis. But the h has not been given in the very beginning. So what we're gonna do, we're gonna replace h with, in terms of that other terms that we have. You know that this one even can go all the way up to here, still r. See? Still r prime, capital R prime. See? Still capital R prime, because that's the radius of the cylinder, anywhere. See? Cylinder. See? Therefore, you can simply say by using the Pythagoras theorem, see? O, A, B, you see? For O, A, B, right triangle. This is how I'm going to write the right triangle. Right triangle using Pythagoras. Pythagoras theorem. I can write this abbreviation later on, see, like that theorem. We have what? OA squared equal OB squared. AB squared, I'm talking about this triangle. This square equivalent to the sum of the squares of these two. OA squared R prime. OB squared X squared. This one X squared. See? You can see, I'm gonna erase this. Okay. Okay. Therefore, your x squared is nothing but r squared minus x squared. R is an r prime squared. Okay, r prime squared. Prime squared. Therefore, H. Therefore, we can use these three dots at the vertices of a right triangle, or the vertices of an equal triangle. So this should be square root r square prime minus x square. That's H. You build up H first. Then come to that cylinder, that small shell, okay? Small shell. See, this shell, I'm going to come back to shell again. This is 2h from here to here. The radius x. That's all we need in order to find the volume of that guy. And we're going to stack those from this point to that point. That would give you the volume of this cylinder, the bead. Okay, I'm going to erase this one for you too. There are too many of these lines over here to make it clear. So this is the bead. So this is the cylinder has been taken out from there. So this is the axis of rotation. So now instead of putting r prime here or r here, I put like that. I'm going to say this is your r prime. And from here to here, this is your capital R. See? The same thing I just locate them at a different place. From here to here R prime, from here to here capital R prime. For certain reason I'm doing that. Now let's get back to that one. Now we have to find the volume of that shell. How do you find the volume of the shell? It's easy if you're gonna this one, cut open. Cut open, look at cut and open. We're gonna have something like this. Cut open. See, this height is 2h, still 2h, still 2h. 2h. This thickness being dx. This one should be what? This length. Length is nothing but the circumference of this thing. That's nothing but the circumference of the shell, which is, how do you find the circumference? 2 pi r, 2 pi x, 2 pi r, 2 pi x. Now what is this? This is a cuboid. See, cuboid. It's not a cube. It's a three-dimensional cuboid. How do you find the volume of the cuboid? Volume of the cuboid is height, width, length. See, height times width times length. Height is how much? 2h. Okay. This is what I'm going to write. start to say multiplication with, which is dx, length 2 pi x. If you rearrange this one, nothing but 2 to 4. I'm going to write 5 next, then h, then x, then dx. Infinitesimally small amount dx. See, I'm going to consider infinitesimally small amount. This is infinitesimally small. See? Infinitesimally small with then h is how much? H we know, okay, but we know h. I'm going to plug in that h here, okay. Can let's replace h 4 pi. H you can remember square root r prime minus x squared. That's another x over here. R squared minus x squared. So this is the volume of the cuboid, or volume of the shell. Volume of the shell. Volume of the shell. I replace h with what we got earlier. Okay. Then we have all the terms, necessary terms, because see, if you do that integral with respect to x terms here, only thing that see, r prime is a fixed value. No, this is a fixed value. It's a fixed, okay? R prime, the radius of the cylinder, sorry, radius of the sphere is fixed, as well as radius of the cylinder fixed, not the shell. There are three things we can consider here. Sphere has a radius r prime, cylinder has a radius simple r prime, and shell has a radius x. See? Is the figure, is the radius. See? These three should be taken into account. See? Everything should be in terms of all these. That's it. Because these are the things that we assume in the beginning. R prime, R capital R prime, simple R prime, and X. See? Now what are you going to do? You simply stack shells from this point to that point. That means your X gonna go from R prime to capital R prime. With that one, if you stack, keep stacking these shells starting from R prime. See, R prime, not X anymore. Okay, X gonna go from R prime. Okay, it's gonna go from R prime. See, somewhere here. See, R prime to capital R prime. If you stack from this point to that point, these kind of a cylindrical shell, that would pretty much cover the volume of the bead. That means you simply integrate this one with respect to x from R prime, simple R prime to capital R prime. That's it. Okay. Now, I'm going to say, I don't need the volume of this shell. Sorry, shell. I need the, therefore, I need the volume of the bead. I'm going to say this one by notation dV. dV. you have to do get the dV and integrate. That would give you the volume of the bead. So that means which is given by capital V. Therefore, capital V is nothing but, I'm going to put dV, replace with this one, 4 pi square root r prime, this one, and integrate. Then we're going to put the bounds for x. X gonna go from, see, simple r prime to this simple r prime, okay? Simple r prime to capital R prime. We set up the integral. We are setting up the integral. It's all about setting up the integral. Once you set up the integral, it's all about now integrating, using the integral techniques and then get this done. Now what? This is a constant. Now this is a constant. Constant. Nothing but, you know this one. 3r. R never going to change. It's a radius of the sphere. Okay. This one also constant. It's a variable. Okay. And this is the variable with which that you're going to do the integration. So that's the operator. So how do you integrate this one? What do you need? Okay. I'm going to rearrange this one in a certain way. I'm going to pull out 2 pi only. Keep r prime to, now we can write like that. You can drop x, okay? R prime to capital R prime to, I'm going to write this one, r prime minus x squared with the aid of this notation. See? Okay. That means you can use the U substitution, but you can easily get this done using what? Using a shortcut. What's a shortcut formula for this kind of integral? I'll write it down here. Okay. So we have already set up the integral. Now we are trying to integrate. So this is our final integral. We are working on that one. This is the picture that we had in the beginning. We don't have to worry about this one anymore. We set it up everything. Limits, bounds, operate, everything we know. This one is something, if you have this kind of way, we know that if you have an integration like this, f of x, you have a function to the power of n, and you have its derivative, inside derivative, right next to that one to integrate. See? Inside derivative. This function has been raised to the power of n. Its inside means its argument has a derivative right next to that one. You can give this one by f of x should be raised to the power of n plus 1 over n plus 1 plus c for the integration of the constant of integration. Okay, you know that constant of integration. In a similar fashion, you can utilize that formula to get this done. Look at you go inside. Oh, I think we are missing here 1x. 1x is missing. We had 2 pi. Okay. You are missing x here. Okay. I noticed that one. Sorry about that one. We can remember we had an x term too. Okay. You can remember, okay? Because I have already erased. I don't think that I can go back to that one. Anyhow, if you use this look like your this is look like your f of x. This is like your f of x. This look like your n. Doesn't matter. It's gonna write that right after this one. Check whether this guy's derivative here. Yes, looks like a 2x, negative 2x. F prime x is negative 2x. But we don't have that one. You can rearrange. At least you don't have to worry about the sign. So I'm going to rearrange this one like this. B, put a negative, and 2 pi. I'm going to write negative 2x here. See? Negative, negative get cancelled up and positive. I just created that one. And R, I can write this way for you to see clearly. I'm going to write this part first. R minus to the half and negative 2x. So this is my f of x. Its derivative is negative 2x. It's over there. If that's the case, you go to the power of that f of x and add 1 to that and divide by the same thing. Okay, so this is going to go from simple R prime negative 2 pi. I'm going to put the answer one shot. R prime minus x squared to the power of half plus 1. Half plus 1. And R prime. This is how you're going to set up the limits. You got the answer. You don't have to put the C because this is a finite integral. See, I utilize that form. Then it's all about, let's simplify a little bit. V. This one 2/3. That 2 you can bring to the top. See, 2 pi. I'm gonna still write like this way, okay? R prime minus x squared. R prime squared, okay? Okay, minus that one. Squared, squared, everywhere squared. Squared. Divided by 3/2 R prime to capital R. Then V is, I'm going to take this 2 to the top. See, I flip 2 pi and this one 2/3. 2/3 times you have R prime squared minus x squared, simple R squared to capital R. So, let's make it a little bit more. V negative 4 pi over 3 capital R prime squared minus x squared R prime. Okay, then I'm going to plug in upper bound and lower bound. V negative 4 pi over 3 R prime square minus R prime square as upper bound minus R square prime squared minus simple r squared for the lower bound. So therefore, I'm left over with negative 4 pi over 3. If this part becomes 0, okay, times negative r squared minus r squared. Then we're gonna go to, see, negative, negative, positive, okay? So 4 pi over 3 r squared, capital R prime squared, simple R prime squared. See, capital R prime squared minus simple R squared, simple R prime squared. See, so we started with capital R prime and simple R prime. So we ended up with that one. Now they have given when, see, when capital R is how much? They say when capital R is 2 and simple R is 1, find the volume. Okay, then we'll set up. Then R equals to, we know that R prime is nothing but how much? 4R. See, 4 times capital R is 2, which is 8. And simple R prime, that we are trying to replace R prime and simple R prime and capital R prime. 3R. Can you remember? 3 simple R. So 3 times this R, see R is 1, which is 3. Now those two values we can easily plug in into this formula. Then you get the volume of the bead. Therefore, the volume of the bead is nothing but V in terms of the numerical value. Okay, 4 pi over 3 R prime squared means 8 squared minus 1, I'm sorry, 3 squared. Simple. Therefore, can we say get the volume? 4 pi over 3, 64 minus 9. Something. Oh, I forgot to write something. Yeah, this should be, can you remember? Yeah, this should be 3 half. What was 3 half, I missed that one. 3 half, I think you can see on your notes, 3 half was missing. But I cannot see when I was writing this one too much. Okay, 3/2 was missing. Can you remember 3/2? Because the 3/2, that one was missing. But you get the rough idea what happened, okay? So 4 pi over 3, 3/2 means here 8 to the second, 3/2 minus 3 to the second, and 3/2, okay? 9 you can rewrite like a 3/2. 64 is when this 2 and this 2 get cancelled, this 2 get cancelled. We would be 4 pi over 3, 8 to the third minus 3 to the third, which is 4 pi over 3. 8 to the third is how much? 8 to the third, this one is 3 to the third is 55, no? 55. That's the answer. Okay, I think that this is a little bit tedious. Rather than going to the second method, I think if I'm going to go to the second method, that you're going to get exhausted. It seems like why you have already exhausted by looking at this one. Yeah, I'm going to meet you in another video to go through the second method for this one. This one means like how to find the volume of the bead when the cylindrical shape has been taken out from the center of a sphere. Okay, until then, goodbye. You have a good day. If you have any question, then you can email to me. My email address, I'm going to make it available later on. Okay, thank you very much. You have a wonderful day. Good night. Bye-bye. Thank you.